Hi, my name is Hosanna Lee from the Media Cloud Engineering team at Netflix. In this presentation, I'm going to describe some of the techniques that we're using to package very large videos. Packaging is the last step in the media processing pipeline. It takes encoded video and audio chunks and packages them into a codec-agnostic container format. The product of Packager is then distributed to the content delivery network of our streaming service or for viewing in theaters. As movies become longer and popular formats use higher resolutions, Packager's product becomes larger and larger. Here are some examples of some recent Netflix movies and their package output sizes. As you can see, the package output of each movie is well over a terabyte. Here is a figure showing the media processing pipeline that we used to use. It takes as input a series of movie clips. From these movie clips, it performs a series of video and audio inspections. And if the clips pass inspection, then they're chunked into pieces and encoded in parallel. When all the encoded chunks are ready, they are fed into an assembler that orders the chunks into a single asset. The assembled asset is then accepted by Packager and turned into a codec-agnostic container, consumable by the streaming service or video player. All of these steps are done in the cloud, with the input, intermediate, and final products in cloud storage. Each component reads objects from the cloud storage using a product called MSFS. MSFS provides a file system interface for reading cloud objects. Bytes are streamed from the cloud object to the reader without the need for any local storage. Output from each component is stored in the cloud for the next component to consume. As you can see from a few slides back, the encoding step is highly parallelizable and scalable. The assembly and packaging steps, however, must be serialized. And that is where and also their outputs are very large. And that's where we try to see if we can make some improvements. Before we get into that, let me first give a brief overview of MSFS. Here's a figure that describes how MSFS works. MSFS is a Fuse module that is installed in the media processing components container. For example, the encoder, the assembler, and packager all have MSFS installed. When the application makes a file system call to read bytes from the cloud object, that call is forwarded by the kernel to MSFS. MSFS then makes the appropriate calls to the cloud storage service to get the bytes. The bytes are then served to the application as they are read from the cloud storage without going through any physical file system. So no local storage is required. MSFS implements caching and prefetching to make the operations more efficient without having to go to the cloud every time the application does a read. There's a blog on MSFS that our team has published a few years ago, and that's included in the slide as a reference in the end of the slides, if you're interested in more details. As we saw from the architecture diagram a few slides back, because all components run in the cloud, the way they pass data from one step to the next is via cloud storage. When a component is done, it uploads its results to the cloud for the next step to consume. This is especially costly for the assembly and packaging steps because of the size of the outputs. Larger outputs mean longer upload times and also bigger disks to hold them before they get uploaded. Here are examples of two large projects and the time it takes to do the assembly and packaging, and the corresponding upload times. As you can see, uploading takes a big chunk of the total job time. Another issue that we must deal with is that we have to process both short and long shows. It doesn't make sense to have one container configuration for all jobs because doing so would be wasteful. Smaller jobs won't need most of the disk of a large configurations, while large jobs will run out of disk space with a small disk. So we end up having two different configurations, one for small jobs and one for large jobs. And we have to schedule jobs based on the show's attributes, such as its length. So how can we deal with large outputs in a better way? So let's first take a look at assembly. As you recall, in assembly, we take all the encoded chunks and put them into a single asset ordered by time. What if, instead of generating a physical file, we generate a virtual file that downstream consumers can treat as a physical file? We call this virtual assembly. We replace the physical file with an index file that provides the same view as the physical file. The index file lists each encoded chunk according to its time order, and for each chunk identifies its cloud location and its offset and size. On the consumer side, which is Packager, we insert an intelligent downloader that can parse the index file and mount the encoded chunks using MSFS, so that from the packager's point of view, nothing has changed. Packager deals with the virtually assembled file in exactly the same way it dealt with the physically assembled files. By eliminating the physical assembly file, we eliminated one of the major components of assembly time. What about Packager? Can we do something similar for Packager? Packager, unlike assembly, we cannot change any aspect of its output because the output is governed by industry standards. So can we eliminate or lower Packager's upload time while preserving the same format? So Packager reads from the cloud without any local storage by using MSFS. And logical next step would be to ask whether it can do the same using MSFS to write its output. However, there are some challenges to this approach due to the way Packager uses the file system. First, when Packager is generating its output, it generates most of the file and then goes back to the start of the file. It requires access to data already written in order to update metadata stored near the beginning of the file. So we cannot just generate output and start and save it to the cloud and just stop there. Secondly, Packager has many options. It supports various options. For example, one option requires writing and rewriting the output in multiple passes. Another option uses intermediary files that are almost as big or just as big as the final output file itself. But these options, it doesn't make sense to upload the contents of the file because it would require too much network bandwidth uploading and downloading the file as Packager makes changes to the data already written. So with these constraints in mind, we have to design a system that can support updates to existing parts of the file that has already been produced, and disallow use of certain Packager options that make uploading the output directly infeasible in terms of performance. Luckily, the Packager options that need to use temporary files or rewriting the whole file multiple times usually refer to small requests. Those requests don't generate very large files, and therefore they don't really need to solve the large disk problem. So we had talked about MSFS and its use of supporting reads of cloud objects. So for Packager, we added a feature to support write operations, and we call this Writeable Sfs. In this feature, we model the file to be saved as a sequence of parts. We maintain a pool of buffers to hold these parts. As the application generates contents of the file, these buffers fill up and get uploaded to the cloud asynchronously. When the application references a part that has already been uploaded, we download the part into an active cache. When the applications make any reads or writes, we translate those requests to operations on buffers in the active cache, the buffer pool, or both. The active cache has an LRU policy to evict buffers to keep memory usage in check. If an evicted buffer was modified, it moves to the buffer pool to be uploaded. This diagram shows how data flows between the various components. Here are some performance results for some large output jobs, comparing Packager using Writeable Sfs, using standard local storage, which is called EBS, and using fast local storage, NVMe SSDs. Packager with Writeable Sfs is about 14% faster than local storage, and is about 2% slower than the faster disk option. So we see that it's not a complete when you're using Sfs. Oops. Although Sfs eliminates the upload step, the read and write operations are also slower due to the overhead of using fields, and also the compute and memory resources are needed to do the background uploads. We also see that using faster disk can eliminate the performance gains of using Writeable Sfs. But these faster disks are expensive, and also using them would mean we have to go back to scheduling jobs based on their output sizes. So in conclusion, by using virtual assembly and Writeable Sfs, we have made significant improvements in the processing speed of a movie, almost 6 times. We have simplified scheduling by eliminating the need to use different container sizes based on show length. These improvements are future-proof against increasingly longer movies with higher resolutions. Here are some links to blog posts that discuss these topics in more detail. Thank you.